I see K that's sticking out. Well, it's not real visible there, but you can see it anchored there. What's C? Circular muscle. What's D? As you know, what's E? That's the actual opening of the nephrostome to meninophrenia. Now, this is the advantage of a multiple choice test. If you saw both choices there, then you should probably pick the nephrostome. But if you only saw meninophrinium as a choice, then you should pick that one. Okay? So that's the advantage of a multiple choice test, is you can see sort of what the answer is being looked for. Okay? Because in theory, you could say, one person might say, oh, I'm going to call that the nephrostome. The other one might say, no, that's a meninophrinium because they're referring to the entire structure. Okay? When the GSI is graded in the past, I would have to tell them, make sure you accept this answer, this answer, this answer. But sometimes they went on autopilot and only accepted one answer, then we have to go back and regrade. So that, again, that's the advantage of multiple choice exam. Okay? And then what's F? Coelom. Yeah? So the question is, how do you tell between a nephrostome and a blood vessel? Is that correct? Okay. So realize the blood vessels that we've seen have pretty much been around the GI tract. And if you notice, this is, it looks like a V almost, an opening, and then it goes down like this. And if you remember, we take the coelomic fluid in as it passes through this tube, and then it goes to another segment and then out to the surface, where the nephridiopore is. So I guess the thing is location-wise. I mean, this sort of looks like, well, this is the blood vessel there. But if you look here, again, on a meninophrinium on a slide like this, I would pick something that's very clearly like this with the nephrostome in view. Okay? I wouldn't pick something where you didn't see this nephrostome, because it's just too hard. Okay? So realize we're looking for ideal representations, not something that would be so. Okay. Let me be careful here. If you've studied it, it should be doable, okay? So I'm not looking for the most obscure possible illustration, but I've had students come to office hours before and say, I never looked at the rat, so I didn't know it was a rat. I'm like, okay. Oh, well, you know. So it's all in perspective, okay? Anyway, let's move on. Another race groups for the mollusca. Here goes to the question you asked earlier, visceral mass. So let's just do some naming. A, mantle or mantle edge. B, shell. C, vagina, I heard no. Okay? This is the lumen of the incurrent siphon, okay? This is the mantle cavity. I need a drink. All right, mantle cavity here. That's what E is trying to illustrate. So again, this is the tricky part when this was a fill in the blank. You know, what do you mean by E? I was trying to indicate the space there or the cavity. So again, on multiple choice exam, you'll see a choice like mantle cavity. Question?
Yeah, for C, how do you know that was the incurrent mantle excurrent?
Okay, because the incurrent siphon leads into the mantle cavity. So if you remember here from the, and it always comes up, so that's why I have this. One semester, literally 20 minutes on this. We're not going to do that this time, though. Incurrent siphon, the cilia on the tenidia create a current. And the current they create is such that they suck water in the incurrent, passes it through the tenidia, out the dorsal aspect, and then out the excurrent siphon. So the incurrent siphon has to lead into the mantle cavity. The excurrent siphon can't lead into the mantle cavity, otherwise you need to get that one-way flow. So the way it's separated is it's separated by this filter, the tenidia, okay? Does that help? All right, so let's do G, the foot. So does it move to the right or to the left as you do this? To the right. What's F? Visceral mass. That's that massive tissue there, okay? What's I? Adductor muscle, anterior, posterior. Anterior. What's D? Tenidia. And the mouth is here with labial palps. Pretty hard to see. H is trying to represent the labial palp, but not real obvious. So I typically wouldn't have asked that on a lab exam because I don't think it's clear enough. Okay? All right. I, again, try to get the best illustrations of things. Question? So the question is, can you see the excurrent siphon in this picture? The answer is no, because the excurrent siphon is behind this one, so it's out of the field of view. So it's dorsal because we're looking from a ventral view. Okay? Now we're going to look from a dorsal view. So now we do see the excurrent siphon here. Now I apologize because this is what happened here. The siphon's sticking off to the left. Here we flipped it 180 degrees, and now the siphon's pointing to the right. I should have probably just taken this image and flipped it so we always maintain the siphon on the same side, but I did not. So here's the excurrent siphon. This has been cut. Normally this would all be closed up, so we would not be able to see the anus, because the anus has to be the distal end of the GI tract, and that anus needs to dump its waste into this excurrent siphon. If it was open to the outside right there, then it wouldn't be working that way. So what we've done is this siphon goes up like this, and we've cut it open so you can see that anus there, okay? So this is the anus right there. This is trying to reveal the lumen of the excurrent siphon because the fluid came into the incurrent. When it passes the tenidia, you can barely see this, not great, but the striations here. Those striations represent like gill-like the filaments that we see in the tenidia. So in here, we saw these gill-like structures of filaments there. This is kind of just barely visible there, but not great. And there's the heart, okay? Any questions? Clams, one of the most difficult structured organisms for those students, and I think that's in part because it's only done as a demo. Now, there are a couple websites that have tutorials where you can click through the clam and identify various things, but they've used a preserved clam, and it's not real great, so that's why I didn't send out the link. A couple people emailed it to me. What was E? Back here? So that would just be the excurrent siphon, okay? 2 questions, yes? Yeah. What was H on the previous slide? H, as I mentioned, is probably the labial palps that transfer fluid to the mouth, but it's not a great illustration of it, so I typically would not have asked that in the lab exam, but that would be one of the few possible things it could be, okay? The mouth would be more in the center there, a dark structure. So the mouth is really hard to see there. Now, when I do the mouth, I typically have a probe move into it, okay? And then your question. To the right? Downward. This one? Yeah. So A here would have been the elastic hinge, okay? Okay? Question. I can't hear a single word you said. So the question is, how much anatomy do you have to know of the things you didn't look at? Is that right? Not much, but you should be familiar with cephalopods. There's a paragraph in the lab manual. That was your exact question, right? Was how much the anatomy of the cephalopod do you need to know? You just need to know a little bit about the shell, you know, whether or not there's a shell present in some of the cephalopods, and a little description that they have closed circulatory system. And so there's one paragraph there. But I would not give you a diagram of a squid and say identify this structure, that structure, okay? All right? Other questions? We used to have students do a squid dissection. We don't anymore. We used to have students actually do clam dissections. We just don't have enough labs. For the echinoderms, make sure you know the various groups. Let's just go over this. Remember the water vascular system. This shows the water vascular system. When you look at the dried starfish that we had in the lab, we've removed the internal tissues, things like that. So what you saw then, I don't have an image of it, was you can see the round ring canal that's there, but you don't see the ring canal, because remember, all these canals are protected by the endoskeleton. So you can infer the presence of it, but you can't see it per se. We have a major porite that leads via the stone canal to the ring canal, and then out in the radius of each arm, laterally to the ampulla, and the 2 feet externally. Okay? The ampulla is internal. And then this just shows you this. Here's the major porite, and these are the spines that give rise to the name echinodermata. Okay? And remember, there's epithelium on the surface, which is why this is an endoskeleton. So in office hours today, a student asked, I asked questions like, are there dermal branchia on the oral surface? Probably not. Wouldn't ask that, but there certainly are lots of dermal branchia here. I don't know how many there are on the oral surface, but I would not ask that type of question. But be familiar with that there are dermal branchia here and pedicellary. Now, with the pedicellary, they probably are distributed more towards the ventral surface, sorry, not ventral, but the oral surface, because of their role in protection. But in the gas exchange, since these are in the substrate, you wouldn't expect to have dermal branchia on the part that's in contact with the substrate, because it would abrade them too much in that. So theoretically, you might think not many dermal branchia on the oral surface, but perhaps pedicellary on the oral surface. Again, I wouldn't typically ask that question, but you can see how you can think it through and rationalize the answer. So I do like those types of questions on exams, where you have to try to rationalize things and put things together that you may not have thought about, but there should be time in the exam. Now, this just shows you right here, 2 feet down here, there's those spines. Here, the dermal branchia are clustered in groups for gas exchange. Are we looking at oral or aboral view? Excellent, oral view. Here we see those spines here modified to protect the 2 feet. Here's the 2 foot there. This is the mouth here. So C, that would be, I'm trying to indicate this entire groove there, so that would be the ambulacral groove. Again, this is where it's advantageous with the multiple trace, because that would be one of the traces. So this would be the 2 feet here, modified spines. This tries to illustrate the mouth there. What stomach gets everted? Cardiac, very good. What stomach is this here? Should be the cardiac, because it's the one closest to the mouth. The pyloric stomach went with the top part. Male or female? Female. Gonads here, huge, orange, salmon color, female. So there's the cardiac stomach, gonads there. Male, gonads white. What are these structures right there? Those ball-like structures. The ampulla. Remember from the diagrams here, we have these ampullae. They look a lot like small pipette bulbs. That's the ampulla, and inside here, on either side of the ambulacral ridge, the ampulla there, lead to the 2 feet externally. Any questions? 13 and counting. Yes? Okay, we don't see the hepatic ceca in this image. They would be aboral relative to the gonads, but we don't see them. You can barely see a little bit dark there. That would be the digestive ceca there and there. But we've cut them and put them with the top part when we removed it, so it's not visible in this orientation, okay? Question? Okay, because the pyloric stomach will be connected to the pyloric ceca. So when you look at an image like this, here, you see the pyloric ceca, or digestive ceca, or hepatic ceca. So what stomach is this? Pyloric. That's why I like the name pyloric ceca here, because it helps you realize this is the pyloric stomach. It is directly connected to the pyloric ceca, / digestive / hepatic, okay? So when you see something like this, here, this is going to be the cardiac stomach. Okay? That's one of those ambulacral ridges. So D is trying to indicate there maybe. What's these structures here? B. Those are the ampulla. The gonads are these C. This is a time of season when it's not reproductive, so the gonads are quite small. Okay? What's F? Okay. Let's go back to this image. It's part of the water vascular system. It's the stone canal. So I'll just point that out to you now again. So we can't see the ring canal. It's covered by the cardiac stomach. And it would also be covered by the endoskeleton. So in the dried starfish, all this tissue was removed. But we still couldn't see the ring canal because it's protected by the endoskeleton. But the stone canal leads to the ring canal here. And what would it lead to aborally? Major porite. All right, this just shows it elevated to help illustrate it more clearly. There's that ring canal there. And you can actually look, if you see how it leads off from the side and then upward? Upward would be to major porite. It leads here into the ring canal. Okay? And there's those spines, the modified spines that we saw on the oral surface. So here's how that cardiac stomach gets everted out through there, okay? And then transfers the nutrients. Yes? What was D? What was E? So in terms of this, in terms of the water vascular system, what would be the water vascular system that we would have seen going around here? Ring, what would be the one that goes along the radius here, like D? Radial, and what was the one that goes side to side? Lateral, okay? Question? So the question is, why don't we see the pedicellary? Because they're microscopic. So to see the pedicellary, they're microscopic. They look like this. Hopefully your GSI demonstrated this. When they're closed, they look like that. They're white. When they're opened up, they look like this. And hopefully they took a dissecting needle, pin in there, and then had it clamped down on it. So this is clamped down, this is open. But they're microscopic, they tend to be white, okay? They're basically 2 hemispheres that come together to make a circle, and when they open, you see those 2 hemispheres out, okay? Yes? The anus is hardly ever visible on the starfish, but you know it's, on the starfish, it's on the aboral surface, okay? All right? So let's go to this. So here, the rectal ceca are here, these brown-like structures sticking out. The intestine's short, we can't see it. It goes from, which stomach is this? Pyloric to the anus. The opening on the other side is that short intestine, we don't see it. But coming off of it, which we can't see because it's buried, hidden by the stomach, are these rectal ceca, okay? So the anus wouldn't be visible. It might have been visible on this very top here. There, but again, it's virtually impossible to see unless it's actually defecating, all right? And then you can see secretions from it, but otherwise, it's too hard to see, okay? Yes? What is C here? It's not a great example of this, but this is probably the stone canal. Doesn't look nearly as good there, okay? So again, I'm going to pick the best examples of this so that it makes it easy to see, okay? This is not a great example of the stone canal, okay? But it was much more obvious than the other ones, all right? Make sure you know this. I'm going to go through here. What stage is this? Egg, larva, pupa, adult, hemi, or holometabolous? Question. Can't hear you. On the previous slide, what is D? This one. So what does D look like it's outlining? It would be the pyloric stomach. It's going around. This is the margin here. So I'm trying to indicate all this here would be the pyloric stomach. So what is E here? Not quite sure what I was trying to do with E. Maybe, just don't know. Okay? Other questions? E, no specific structure. Okay? All right? It wouldn't be on the exam. Okay? All right? Question. I couldn't hear a word you said. Give me an example of what? Tegmatization is a fusion of head and thorax. So in the crayfish, you see the abdomen, and then you see the head and thorax are fused. So let's just look at an image of a crayfish that hasn't been dissected, which I may not have one. Yeah, spider, but I don't know if I have a good image of that. So anyway, if you remember with the crayfish, I don't have an illustration of this. It had the head and the thorax. You didn't see a boundary between the two. So that's an example of tegmatization. Fusion, okay? All right, be able to sex them? Yes, question. We have 6 minutes. We'll see what we can do. Nerve cords, yep. The question is, are there advantages of having ventral versus dorsal nerve cord? Not that I'm aware of. There potentially are some, but just realize the location is ventral versus dorsal, some of the groups, okay? But I don't know of any particular reason why it'd be advantageous to have ventral versus dorsal, okay? Yeah. Now, in our case, we have protected by the vertebral column, so that's advantageous for protection, okay? All right, so just give it, what gender is this? What sex? Female? Okay, so let's just do A. Crop. B's trying to indicate these white tubes, let's say. What would be the white tubes? The white tubes would be the tracheals. They're throughout, filled with gas. If this arrow was slightly down further, what would this structure be? Gizzard? Gastric ceca or digestive ceca? Again, what's D here, this white tube? Tracheals. Again, this is where it's difficult to tell. Are you pointing to the midgut or are you pointing to a tracheal? Okay? So again, in a fill-in-the-blank sort of thing, I have to tell the GSIs, make sure you accept multiple answers because the student may not know specifically which answer to put, okay? That's just fair to you. Okay? What's F? No pigeon tubules. What's G? Ovary or ovarials. We accept either one. What's H? Gastric gland. What's I? Another ovarial. What's J? This one in the middle. Ventral nerve cord. What's K? Tracheals. Remember, all these silvery tubules around here, those are all the tracheals because that's the respiratory system. They have to subdivide so they're close to every cell. Okay? And then what would L be? Fat. A little easier to see in a close-up. What's this? Notice how this tube is bigger here? What would it lead to eventually, externally? Spherical. So what's this? Crop. Why are there more tracheals on this gizzard than on the crop? It's more muscular. It needs more oxygen, right? It's churning and breaking the food down, right? Whereas the crop is pretty much storage, although it does eject food to the gizzard. You don't need a lot of muscle, so you don't need a lot of oxygen-rich supply. This? No pigeon tubules. What's this? Conglobate. What's this? Yep. Conglobate and accessory glands. For the crayfish here, what sex? Female. What are these structures here? Mandibular muscles. They attach to the mandible. Internally, they would have attached to the exoskeleton, and that's how they generate their force. Because they have 2 anchor points. One anchor point on the inside of the exoskeleton, the other anchor point on the mandibles for fragmenting the food. Yes? The question is, how do you tell this is a female? This is the ovary here filled with all these black, large eggs. Whereas the male would have microscopic sperm. The testes are obvious what the vas deferens is. And I want to show you that for sure because there weren't a lot of... We had little stories of male crayfish on Tuesday, so I want to make sure I get to the male. Okay, so right now, I definitely want to go over this right now in the minute or so that we have. This is a male. The easy thing to tell is you don't see the ovary filled with those eggs, but furthermore, this white coil here, which is large, is the vas deferens. So the male crayfish are easy to identify for several reasons. One is they have this large white coil tube, the vas deferens, and they, of course, lack an ovary filled with large eggs. Okay? And this just shows you here, this is digestive gland there. This is the cardiac, ossicle, pyloric. The gastric mill's inside there for fragmenting food. What sex is this? Female. Those are the eggs. There's openings are the ostia that lead into the heart. Here shows you this cardiac ossicle here. So to the right is anterior. This is the pyloric. And notice the orientation. Cardiac is closest to the mouth, which is what we saw with the starfish, right? Cardiac's closest to the mouth. And there's the gastric mill inside there. We've cut into this tissue to see the gastric mill inside. Okay? Your question. Okay? So the question is, how can you tell this is the cardiac ossicle and this is the pyloric, basically, right? The cardiac ossicle is much thicker and much bigger than the pyloric. This is about, 2 times bigger than this, and also a couple times thicker. So that makes this the cardiac pyloric. Okay? Strictly size. Okay? Any other questions? And then here we see the gastric mill cut, and this is the gastrolith there for storing calcium. Green gland there. Side view there, the green gland. And then we don't have much time to do the heart, so let me just do one thing quickly here. I'm going to go over the next 3 images, and I apologize. I'm glad you asked questions, but we pretty much are running out of time or have run out of time. So here's the common wall of the septum. Is this left or right ventricle? Left. Huge thick wall here versus this. That makes this left, right. What valve? Bicuspid, tricuspid over here. Now in terms of arteries versus veins, always questions about how can I identify an artery versus a vein. Arteries have a lot of elastic tissue on them, and they tend to remain open, and they are white. If I stuck a probe in an artery, and that probe went into the right ventricle, what artery was that? Pulmonary artery. Because the right ventricle pumps blood via the pulmonary artery out to the lungs. And if that probe went into the left ventricle, it would have been what artery? The aorta. And then I could ask you what valves would that probe have gone through, and what would they be? Semilunar valves, whether they were in the aorta or in the pulmonary artery. They wouldn't have gone past the bicuspid or the tricuspid because that probe would have to go from an atrium into a ventricle, okay? And the veins tend to collapse and be red, okay? And this is just trying to illustrate that. There's an artery here, and then this is leading into the right ventricle, so what artery is that?